In this clip, we'll look at the solution of a 1D kinematic problem. It's a typical one involving free fall. So here's the statement. You throw a French fry upward at 15 meters per second from a height of 2 meters. You can neglect air resistance. First, we will focus on part A. The fry is caught on its way down by a seagull at a height of 5 meters. How long had it been in the air? Okay. So please hit pause, try to solve this problem if you haven't done so before, and then come back when you're ready. When you try to solve such a problem, the first thing is to try to identify which model you're using. In here, there are a couple of assumptions that we are making and that it's nice to make explicit. First, we're assuming that the fry is actually just a particle, so we will look at it as just a single point. Second, we're neglecting air resistance. And finally, we have to recognize that it's a free fall problem, so we can use the acceleration due to gravity in order to solve it. The second step in the analysis is to visualize what's going on. I strongly advise you to draw a picture, draw something. Motion diagrams can be really helpful to understand what's going on. So if this is the ground, we know that the fry is starting about 2 meters above, and it's moving pretty fast at first, but as it rises in the air, it's slowing down until it reaches a max height, and then it's falling back on the same path. I'm putting it a little bit on the side in here to make it clearer. And at some point, it is caught by the seagull, so that stops the motion. So that's the first step, okay, just to help you see what's going on. Once this is done, I want you to always set your reference frame, okay, your coordinate system. So your coordinate system consists of two things. First, you have to choose your origin. You can decide to put the origin at the ground or here. We could also decide to put it where the fry was initially. So let's say that we put it at the ground this time. And then we have to choose the positive direction. And to indicate the positive direction, we just put the arrow and the axis label in the direction that is positive. So in here, up is positive. When this is done, the next thing is to go and hunt for the 6 variables that we always have to find whenever we're dealing with 1D problems. So in this case, we want to go back to the problem statement and try to extract as much information as possible. The first number that we have when we get in here is the 15 meters per second. Just from the units, we know it's a velocity. And we know that this is the initial velocity because that's the velocity at which the fry is thrown. So we will take it as 15 meters per second. We know it's positive because it's pointing in the same direction as our positive axis. Then from a height of 2 meters, so that's also an important information. That tells us what is the initial height of the fry. The fry is caught on its way down by a seagull at a height of 5 meters. So we know that the final height will be equal to 5 meters. The final velocity is not given. Be careful, it's not equal to 0 in here. Okay, even though the seagull is catching it, that does not, we are looking for the motion just until the moment, a fraction of a second before the seagull is in play. So we don't know this one. Acceleration, we know that this is free fall, so we know it will be 9.8 meters per second squared. Okay, but be careful, the acceleration is pointing downward. That's where the force due to gravity is acting. So we need to have an extra negative sign in here. And finally, the delta t is also unknown. Since the question is asking how long is the object in the air, we don't want to use the final velocity, but we do want to use the delta t. So we'll be looking for an equation that will provide us with these features. Then we are ready to try to solve. So we have to identify the equation that can help us in here. And from what we just discussed, we know that that equation will be excluding the final velocity from the equation. So the equation we want to use will actually be the one that tells you the final position given by the initial position plus the initial velocity multiplied by delta t plus 1/2 times the acceleration times delta t squared. So we already have all that information, so it's just about plugging the values in. Y final will be equal to 5 meters, the y initial will be equal to 2 meters. The v initial is simply equal to 15 meters per second. Delta t unknown. And then we have the 1/2 ay. I remind you that ay is equal to minus 9.8. So when we take the half, we will get minus 4.9 delta t squared. Okay. And we have to solve that equation. You should recognize at that stage that you cannot just use algebra to isolate delta t. You'll actually need to use the quadratic equation. So to do so, we need to make sure that we have the other side that is equal to 0. So this will become 0 is equal to minus 3 plus 15 delta t minus 4.9 delta t squared. Here I want to note that I dropped the units because I knew that I would end up with the quadratic equation. In general, it's a good idea though to keep track of the units so that you can spot mistakes more easily. So quick refresher on the quadratic formula or quadratic equation. What you want to do when you get this is it's usually of the form ax squared plus bx plus c is equal to 0. And in that case, we know that x will be equal to minus b plus or minus the square root of b squared minus 4ac, all of that under the square root. And then we have to divide all of that by 2a. So in our initial equation, this in here is equal to c. This plus 15 is the b. And finally, the minus 4.9 will be equal to the a. So we can rewrite the equation just using these. So we have that delta t is equal to minus 15 plus or minus square root of 15 squared minus 4 times minus 4.9, which is the a, times minus 3, which is the c. And all of that will be divided by 2 times a, so 2 times minus 4.9. Okay, so if we expand this portion in here, we will get minus 15 plus or minus 15 squared is 225. Minus 4 times minus 4.9 times 3 will be minus 58, 0.8. And then we want to divide all of that by minus 9.8. We'll just continue here on the right. So then we have our delta t is equal to minus 15. And once I take the square root in here, I will get 12.89. So plus or minus 12.89 divided by minus 9.8. And I have to use both roots, so I will have two answers. So the first one will be with using the positive sign, so minus 15 plus 12.89 divided by minus 9.8. And the second one will be minus 15 minus 12.89 divided by minus 9.8. And once you do all of that, you get two possibilities. The first one is that delta t is equal to 0.1215 seconds, and the second one is that it's 2.85 seconds. Sometimes one of the root will be negative, and we know that then the delta t is not that root. But in here, both roots are positive, so you have to be a little bit more careful about what's going on. And what happens is that the fry is starting up and coming back down. So it actually passes the 5 meter height both times, or two times. First on this side and second on this side. So the first value that we get for delta t is when the fry is at 5 meters, but on the way up. While the second one is when the fry is at 5 meters, but on the way down. So the one we want in here is really the second one, the 2.85 seconds. And that solves part A. Answer part A, I'm sorry. As always, we should assess our answer. So 2.85 seconds for a fry going up and then coming back down sounds credible. And also, are we indeed answering the question? How long has it been in the air? Yes, we do. So that's fine. So we can move on to part B. In part B, we are looking for the velocity of the fry just before it is cut. So we will start from all the information that we already found in the problem. That we'll just bring in here. So we already have initial and final position. We have the initial velocity. We also have the acceleration and now the delta t. So what's missing is the v final. There's an easy way to get there using the time. I want to actually show another method that is a little bit more complicated here because I want to show you something. So I will actually use the equation that is stating Vf final y squared is equal to V initial squared plus 2 times the acceleration times the change in position, or change in the displacement, so y final minus y initial. So if I want to do this, and what I'm solving for is Vf final, that's easy. I'm just taking the square root of what's on the right. So let's put the numbers in there. So we will have V initial squared, which is just the 15 meters per second squared, plus 2 times the acceleration is minus 9.80 meters per second square. And then we have y final minus y initial, and this will be 5 meters minus 2 meters. So we can do the math in here. This one will give us 225 meters squared over a second squared. And the second term is just 2 times 9.8 times 3, which will give us 58.8. Again, meters times meters, so meter square, and then second square at the bottom, which makes sense. However, I messed up my sign in here. This should not be a positive sign, but rather a negative one. Sorry about that. And after we get this, we can do the square root, so that we will get that Vf final is equal to the square root of that thing, and this will give you 12.9 meters per second. Now, this is where we have to be careful. Whenever you take a square root, there's always 2 roots that are possible. So in here, it could be either plus 12.9 or minus 12.9. We have to choose the proper sign. And because we know that in this case it's on the way down, we know that we have to take the negative sign. So when we write our final answer in here, okay, it will just state that the V final on the y-axis is just equal to minus 12.9 meters per second. Okay, don't forget that sign. Part C now, what is the max height reached by the fry? So you have to be careful. There's often a tendency to restart from the information that we already have. But that information is no longer valid. So for instance, the delta t is no longer equal to 2.585 seconds. And the final height is no longer equal to 5 meters either. And if we looked also at the V final, we just found a couple of seconds ago that it was minus 12.9 meters per second. Well, this is also no longer applicable. So you have to be careful. Things will change a little bit. What stays the same are the initial condition and the acceleration. But when the object reaches its max height, remember our motion diagram? This is when it's changing direction. And as it changes direction, when it reaches the max value in here, the Vy will actually be 0 at that moment. And that's the key. When we're looking for the max height, we want to use a Vy final to be equal to 0. Okay. After this, you can get to the equation a number of different ways. Probably the easiest is to use, once again, the equation we had in the previous, in part B, which is just the one with the squares of the velocity, and just recopying it in here. So this will now be my y max minus y initial. And I want to say for this, to solve for this, the V final we said was 0, so this will simplify things a little bit. So when I want to isolate my y max, so I will take my V initial on the other side, which will become minus V initial squared, is equal to 2 times AY, y max, minus y initial. I divide by 2ay on both sides, so it becomes minus vi squared divided by 2ay is equal to y max minus y initial. And finally, I get that y max will be equal to y initial plus, vi y squared divided by 2ay. You might be scared by this minus sign in here, but remember that the ay is actually a negative number. So when we plug everything in here, we'll get 2 meters minus 15 meters per second squared divided by 2 times minus 9.80. And once we solve for this, we get 2 meters plus 11.5 meters. So the total height for the y max will be equal to 13.5 meters from the ground. And not surprisingly, this is bigger than the final height that we had previously, that was of 5 meters. Finally, the last step is to draw the graphs. So I think it's actually easier to start with the AY graph. And this one we know is just a constant value. And actually we know what constant value it is. We know it's minus 9.80, okay, in meters per second squared. For the velocity, we know that the velocity starts positive and eventually it ends up being negative because the fry is falling back down. And we know that the slope will be constant because the acceleration is constant, and we know that the slope will be negative because the acceleration is negative. So we'll get something that will look like that. And for the y versus t graph, we get a nice parabola. Parabola should have a slope at the beginning for the tangent line that is positive because the velocity is positive. At some point it will reach the max point where the slope of the tangent line will be 0, and then it will fall back down, but it will not quite go as high on the way back than it did on the way up. So we're looking for something that will look like this, and this is where the fry would be cut. Sorry this clip was a bit long. I'll try to be more concise later or next time. Thanks.